Hello everyone. Welcome to the course of Finite State Machines. This video is brought to you by Newton's Group of Institutions, Macharla. This is Aravind Yegireddy from the Department of Computer Science and Engineering. In this video, we will study about the finite state machines. A finite machine, which is also called as an finite automata. A finite automata which is used to recognize the patterns. It is an simple idealized machine. It is a mathematical model of computation and it is an abstract machine which can be used in exactly one of the finite number of states at any given time. The finite automata is divided into two parts. One is finite automata with output and finite automata without output. In finite automata with output, we again have two categories. One is a Moore machine and the Mealy machine. And in finite automata without output, we have three categories. One is a deterministic finite automata, DFA, non-deterministic finite automata, NFA, or epsilon non-deterministic finite automata represented with the epsilon NFA. Now let us see all one by one. Before discussing, let us see the two important properties of the finite automata. They are: finite automata is the simplest model of computation. And also, finite state machines have a very limited memory. So here, these are the two important points we should always keep in the memory before studying anything about the finite state machines. Now, let us discuss the DFA with a simple structure of a DFA diagram. So here this diagram shows out the structure of the deterministic finite automata or DFA. Can anyone say what are these? We have some circles, we have some edges here with some arrows pointing here and there, and we can see some labels like 11000001, so on. So what are all these? So let us see what all these means. First, let us understand one by one. These circles, we call them as states. So these are being represented by A, B, C, D. So these circles, we call them as states. Next, we can see some edges going from one state to another state. And these edges, we call them as transitions. So what does these transitions mean? Suppose that we are at state A. This is an edge with a label 1. And these labels of edges is called as an inputs. So suppose if we are at state A and we get the input as 1. So from state A, we can go to state B with input 1. And if we are at the state A and we get the input 0, then we go from state A to state C. Suppose if you are at state C, if you get the input 1, you go to D. And if you are at state C and if you get the input 0, we go to the state A. So here these labels are the inputs and the circles are the states. So this shows how the state transmits from one state to another after getting some input. So here if you can notice, there is some differences between the state A and state D. And in the state A, we can see a arrow which is coming from nowhere into the state A. So what does this mean? So here we are getting an arrow into state A from nowhere. So this means that the state A is the starting state. So state A is the initial state of the deterministic finite automata. Now, if you look at the state D, it is something different from other states. What is that? Every other state we have single circles. But here in the state D, we have double circles around it. So what does this mean? So whenever we see a double circle, it means that it is the final state. That is, it is the terminating state. So here in this case, D is the final state of the deterministic finite automata. So now let us go to the formal definition of the deterministic finite automata. Every DFA can be defined by using 5 tuples: Q, sigma, Q naught, F and del. So we can define the DFA using these 5 tuples. Now let us see what are these 5 tuples means. First, Q is set of all the states, and second, sigma, which represents the inputs, and third, Q naught, which means that start state or the initial state, and fourth, F, which is the set of the final states. It means that we can have more than one final state. When I mean that set of final states, we can have more than one final states. And the fifth one is a delta. So what is a delta? Delta means a transition function that maps from Q cross sigma to Q. Now with this example, let us write the rules for the 5 tuples. First, Q. So what are the values of Q? Here, Q is nothing but it is set of all states. So what is set of all states here? It is A, B, C and D. And what is our sigma? Sigma represents inputs. So here our inputs are 0 and 1. Next, Q naught. So Q naught is the start state or the initial state. So here our start state is A. Now F is the set of final states. So in this case, we have only one final state. So D is the final state. And now coming to the delta, delta is a transition function from Q cross sigma to Q. So to demonstrate this, let us use a table to explain what is a delta. So in top part, let us take the inputs 0, 1 and let us have the states here A, B, C and D. Suppose if I am at state A and got the input as 0. So I am at state A, got input as 0. Where I go? We go to state C. So here we write C. And suppose we are at state A and we got the input as 1. Then we go to state B. If I am at state B and got the input as 0, then we go to state D. If we are at B and we got the input 1, then we go to state A. If we are at C, we got the input 0, we go to state A. If we are at C, if we get the input 1, we go to the state D. If we are at D, if we get the input 0, we go to state B. And at D with input 1, we go to the state C. So this is the basic structure of DFA. I hope all of you understood the concept. So here, now let us see what is the deterministic finite automata with an example. So here, in order to understand the NFA and DFA, we have to see the properties of the DFA, which will help us to differentiate the difference between the DFA and the NFA. So it comes from the word determinism. Deterministic finite automata comes from the word determinism. That is, we can determine the things. So in a DFA, given the current state, we know what the next state it will be. So if I am in state A, I know that I will go to state B if I get the input 1, and I know that I go to state C if I get the input 0. So it has only one unique next state. So you don't have any choice in deterministic finite automata. So it has no choice or it has no randomness. And it is very simple and easy to design the deterministic finite automata. Now, let us see an example. Let us see the set of all strings that starts with the 0. So our language L is equal to set of all strings that start with the 0. So here our grammar will be 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, so on. So here every string is starting with the string 0. So here how we can draw the transition diagram for this particular thing. So here into A we are having an arrow from nowhere. So this A is the start state. And from A, if with the 0 input, I am going to B where B is my final state. So 0 is the final state. Now again 0, 0. So I have gone to B with the 0 as input. And from again with the 0 as input, again I take a loop and I go to B where B is the final state. So 0, 0 is also is within the string, within the language. 0, 1, so 0, again 1 within the loop of B. So here we get the grammar 0, 0, 0, 0, 1, 0, 0, 0 all. Now coming to here in the state A, if we are getting the input 1, we go to the state C, and at state C, whether it is 0 or 1, we have a loop over C. So we always be at C when the initial input is 1. So we can never reach it to the final state. So this is the machine which is going to have all the strings that start with the 0. Now let us see what is non-deterministic finite automata. So here take this example. So now what is a non-deterministic automata? It comes from the word non-determinism. And what does this mean? So in NFA, given the current state, there could be multiple new states. So if you take this example with I am at state A with 0 input, I can go to A again or I can go to the state C. With from A with input 1, I can go to B or I can go to D. So I have multiple states. From current state with the same input, I have multiple states. So the next state may be chosen at a random. And all these next states may be chosen in parallel also. So here, if you can see, we can see an state with epsilon. With an input epsilon, we are going to go from state A to state E. So what does this epsilon means? So here epsilon means an empty string. So this means that the state can also accept an empty string, and on taking this empty input, it can go to another state, that is state E. So the concept of epsilon only comes in the non-deterministic finite automata. If you see that if you are going from one state to multiple states for the same input, then we call it as an non-deterministic finite automata. Now, let us try to understand the non-deterministic finite automata with an example. Then we can go to the formal definition of NFA. So here we have an example of NFA, which is actually a machine which accepts set of all strings that end with 0. So how can we say that if you see this example on getting 0, it comes to B, which is the final state represented by double circles. So now by seeing this figure, let us try to figure out the difference with the DFA. In this, you can see that A is the starting state. By this arrow which comes from nowhere, we can say that A is the starting state. So here if you see, A on getting the input 0, it is staying in A itself, or it could go to B. So there are multiple next states. So A on getting the input 1, it stays in A itself. So now coming to B, let us see what happens if B gets the input 0 or 1. See here, what is this? Is this wrong? Because the B with input 0 and 1, there is, it's not going to any state. So can we say that it is incomplete? No. In NFA, actually we can leave like this. So here in NFA, we can be in a state where with on some input we don't go or we don't move anywhere. So it is perfectly legal to leave the states like this without mentioning anything. So actually this means that this state does not go anywhere. So in case of DFA, it is not legal to leave the state like this, but in NFA it is a legal. So from this you can say that it is also very easy to design an NFA when compared to that of DFA. So now let us try to give the formal definition like DFA. It also has the 5 tuples which are Q, sigma, Q naught, F and delta. So using these 5 tuples, we can define the NFA. Now let us see what are these 5 tuples. And they are all just similar to your deterministic finite automata DFA. First, Q is nothing but it is set of all states. And second, sigma is the set of inputs. And Q naught is the start state or the initial state. And then F is the set of final states. So here F is the set of final states. And delta is a transition function that maps Q cross sigma to what? So here we need to see what is the answer here. We will try to find out what is this. So now let us try to write the values of this example. So in this particular example, what is Q? Q is set of all states. So here the set of all states is A, B. And sigma is the inputs. So what are the inputs here? 0 and 1. And Q naught is the start state. So how do we know that which is the start state? The state that is pointing by an arrow that comes from nowhere. So here A is the start state. And what is F? F is set of final states. So here we have only one final state with a double circle around it. That is B. So B is the final state. Now, what is a del? How do we find the del value? Let us see. State A on getting 0, it goes to itself. So here state A on getting 0, it goes to itself. Okay, state A on getting input 0, it goes to B also. And state A on getting input 1, again it goes to itself. And state B on getting input 0, it does not go anywhere. So we represent this with a pi. So state B on getting 0, it goes to pi. State B on getting the input 1, it does not go anywhere. So we represent it with a pi once again. So we see that given a state, when it gets a particular input, it can either go to one state or more than one state. So we can see that A on getting the input 0, it can go to two states A and B. So here we have four possibilities. So for this example, A and B, it can go to A, B, AB or pi. Four possibilities. That is 2 power 2. So here we have 2 power 2 possibilities. Suppose if we considered one more state C, then the different possibilities are A, B, C, AB, AC, BC, ABC and pi. So here we have 8 possibilities. That is 2 cube possibilities. So 2 states we have 2 power 2 possibilities. 3 states we have 2 power 3 possibilities. So we can say like this. If we have n states, we have 2 power n possibilities. So here delta is the transition function that maps q cross sigma to 2 power q, where q is the number of states. So this is the formal definition we could give to the non-deterministic finite automata. Now let us discuss this epsilon NFA. So here this symbol we call it as an epsilon symbol. So epsilon is used to represent the empty symbols or null symbols. That is, it is used to represent nothing. Now let us see the definition of an epsilon NFA and see what is the difference between the NFA and the epsilon NFA. Our regular NFA is defined with 5 tuples Q, sigma, Q naught, F and L, wherein epsilon NFA also we have the 5 tuples which are used to define the epsilon NFA, where Q, sigma, Q naught, F are same as of regular NFA, and the only thing that is different is that the del here. So let us see how is it different in regular NFA. Here del was defined like q cross sigma to 2 power q. So here in this case q is nothing but it is set of all states. Sigma is set of inputs. Q naught is the initial state or the start state. F is set of final states and delta is the transition function. So here let us see the difference in the regular NFA del, how it is defined and how it is being defined in the epsilon NFA. So here the inputs are A and the Q is having 2 states, one is A and B. The inputs are 0 and 1. The initial state is A. The final state is B. Now let us see what is the transition function. Here it is Q cross sigma something tends to 2 power Q. Here something is there. What is that? So here the transition function in our regular expression is something like Q cross sigma tends to 2 power Q. That is, any state on getting any input, it can get any of the 2 power Q outputs. So this was for our regular NFA. But in case of epsilon NFA, what we have is Q cross sigma union epsilon tends to 2 power Q. The meaning is that Any state on getting an input or no input, it can go to any of the 2 power q outputs, which is called as an epsilon NFA. Now, let us see the Mealy and Moore machine. So these are the two models which are being developed for representing the synchronous sequential circuits. So here the first one, that is Moore circuit or the Moore state machine. So here the first state machine is an Moore circuit or the Moore state machine, and the second one is Mealy circuit or Mealy state machine. So now let us see what are the two models and how they are different from each other. So they differ only in the way in which the output is being generated. As we know that the sequential circuits consists of the combinational circuits and a block of memory. So here we have a block of memory which is nothing but resistors. We know that the resistors are made up of flip-flop. So a memory block is nothing but it is our flip-flop. So here if we need to calculate the output, it may depend on the input and definitely the present state also. But sometimes it does not depend on the input. In that case, we call it as an Moore circuit. So a Moore circuit, the output is the function of the present state only. So here the output does not depend on the present current input. Whereas in case of the Mealy circuit, the output is the function of the present state as well as the input. So this is the main difference between the Mealy machine and the Moore machine. Now let us first discuss about the Moore state machine. So here if you can see in the block diagram of a sequential circuit, this is called as an combinational logic. That is the next state combinational logic. Sometimes we also call it as an next state decoder. So here this we call it as an next state decoder. The next state of the sequential circuit, so here which depends on the logic that is being given here. So whatever the next state is stored here in this memory. And one more interesting thing what we see here is, and one more combinational logic. So here one more combinational logic we can see here, depending on which the output is being generated. And here you can clearly see that the output is the function which is based only on the present state. So here the output is dependent only on the present state, and there is no impact of this input which is directly on the output that is being generated. So here the input has no direct impact on the output that is being generated. So here the output is only the function of the present state. So this is the model of the Moore state machine, and now let us go with an example. So now let us discuss the Moore machine with T flip-flop with some gates. Now let us see what is the next state combinational logic, and let us also see the output combinational logic. So here this one, these are two circuits, we call them as next state combinational logic. So you can see that here the input is A, where A is given, and though these two logical gates, this is our next state logic, and this is OR gate, which is the output of the combinational logic. So now we have to find out the value of Y. So the value of I depends on two factors. So if you can clearly see, it depends, the one factor is QA and the other factor is QB bar. So here you can see that these two inputs in this OR gate, and the output Y is the output from this OR gate. So we are giving two inputs. The one input is QA and the other input is QB bar. So Y is equal to QA plus QB bar. QA plus QB bar. So there is no A in this particular equation. So Y is independent of A. That is our output. So it is clearly a Moore model. Now coming to the example here. So here we can see the original state diagram. Now we need to draw the Moore state diagram using the original state diagram. So here we are having four states: 0, 0, 0, 1, 1, 0 and 1, 1. Here the first, this one is the input and this one is the output. 1 is the input, 1 is the output. 0 is the input, 1 is the output. 0 is the input, 0 is the output. 1 is the input, 0 is the output. 0 is the input, 0 is the output. So here we are going to write the inputs and outputs depending on the function that is being generated. So now this is our original state diagram, and we need to draw the Moore state diagram using this original state diagram. So here, to draw the Moore state diagram, what are the changes we have to make? So we have to remove the output and write it inside the state. So here what is the output? 0 is the input and 0 is the output. 1 is the input, 1 is the output. 0 is the input, 1 is the output. So here 0 is the output. That output we need to write inside the state. Here 0 is the output. That output we need to write inside. So here our Moore state machine will be something like this. So we are removing the outputs, and this output is being removed and placed here. This output is being removed here and placed here. This output is placed here inside, and this output is removed and placed inside. And remaining whatever the inputs are there, we are going to write it as it is. So this is the diagram, how we can convert the original state diagram into Moore state diagram. Now coming to the Mealy state machine. So here, if you remember, the difference between these two machines is the way in which the output is being generated. So in the case of the Moore machine, the output is the function of only the present state. But here, whereas in the Mealy state machine, the output is the function of the present state as well as the input, current input, present input. So here the output, what we are going to generate, it is going to have direct impact of the present input, current input, what we are giving. So here the difference what we can notice between the Mealy machine and the Moore machine is, in the Mealy machine, the output depends on both upon the present state and the present input, whereas in the Moore machine, the output depends only on the present state. And in Mealy machine, generally, it has fewer states than compared to that of the Moore machine, whereas in the Moore machine, we have more states when compared to that of the Mealy machine. And in Moore machine, the value of the output function is a function of the current state only. So it has no impact of the present input. Whereas in the Mealy machine, it has the current state at the same time present input also. So here the Mealy machine, which reacts faster to the inputs. So when I say that it reacts faster to the input, that what I mean is it gets executed in the same clock cycle. Whereas the Moore machine logic is required by the decoder. So here the output gets delayed by one clock cycle. So here, if you see the example of the T flip-flop, the same thing, if you can notice here, see we are giving 3 inputs to this particular output combinational logic or gate. So here the y value is, if you can see here, a plus qb bar plus qa bar. So y is equal to a plus qa plus qb bar. So it depends both on the present state and the present input. So this is the difference between the Mealy machine and the Moore machines. Now for the input string 1010, let us see what will be the output that will be generated for this particular original diagram. So here if you can see that the original state diagram is having one going from Q1 state to Q2 state. It has a two states and with one input and B as output, 0 input and A as output, 1 as input and A as output, 0 input and B as output. Now, if the input string is 1010, then what will be the output? So I am at state Q1. If the input is 1, it goes to Q1 itself with an output B. So answer will be B. Then with the input 0, so from Q1, if the input is 0, we go to state Q2. So now I will be at state Q2. What will be the output? A. So BA. Next with input 1, from Q1 state, I will be at 1. I will be at Q2 state only with output A. So BAA. And with the out for the input 0 at Q2 state, it goes to Q1 with output B. So answer is BAAB. Now if I need to convert this into the Moore machine, what I need to do? I need to write the inputs, outputs inside the state. So my Moore machine will be something like this. So now I am at state Q1. So when I am at state Q1, what is the output? B. So B with Q1 with input 1, again the output is B. So BB. With Q1 with output input 0, I will be having an output A and I will be in state Q2. So BBA. With Q2 and input 1, again A. So BBAA. With Q2 and input 0, again I will be at state Q1 with B. So it is BBAAB. So here I have 4 inputs. Here also I have 4 outputs, whereas here I have 4 inputs, but the outputs are 5 in the Moore machine. So that's all for now. Thank you very much for listening to my video. If you like this video, please subscribe to my channel and press the bell icon for the latest notifications. Thank you, one and all.